Okay, welcome to the C4H Weathering Change Seminar Series. Today's speaker is Melissa Furlong from the University of Arizona. She'll be presenting heat waves during pregnancy and neurodevelopment outcomes in Arizona. I would like to share a few announcements before we begin. First, attendees will be muted until the Q&A portion of the seminar at the end, where you will then be able to unmute yourself and ask questions. During the presentation, you can add questions to the chat. You will receive an email after the seminar concludes that will include an evaluation link as well to the C4H website and the YouTube playlist for upcoming and previous recordings. If you would like to join the C4 membership list to receive emails about these events as well as the monthly newsletter or other activities within the center, you can add your email address to the seminar's evaluation, or you can complete the form that Jessica will post in the chat. I'll turn it over now to Melissa for her talk.
Hi, everybody. Thank you for coming. I am an assistant professor at the University of Arizona, although I just got my tenure decision on Friday, so we'll be an associate professor starting in July. And today, I just want to give you a little context for the talk. So as more people are doing research on heat and temperature and associations with health, these models are becoming a lot more common, but there are lots of methodological challenges that have not necessarily been solved to help facilitate those models. So temperature, I think when we all initially started to model temperature, we thought it would be fairly similar to air pollution in that we have these pretty good national models of ambient temperature, and we could link them to various health outcomes data to look at associations between heat and extreme temperature and outcomes. But it's a little bit different from air pollution in that air pollution is pretty tightly regulated. And so the geographic variation, there is some geographic variation in air pollution levels, but not as much as there is with temperature, right? And temperature varies very strongly across the United States. So we have this geographically diverse data with extremely heterogeneous exposures. And so for RP20, the research project that I'm leading, we were modeling heat waves with preconception, modeling heat waves during preconception and pregnancy and associations with neurodevelopmental indicators in childhood. And we were doing it in the state of Arizona. And so if you just look at Arizona, you can see that the temperature distribution is pretty heterogeneous in terms of average exposures. And we encountered a lot of questions during this modeling journey. And we wanted to know what were the trade-offs of different heat models and different modeling choices in terms of exposure misclassification and how well they captured different effects. And so in this talk, we have two parts. In the first part, I'll be taking you through a simulation assessment. And in the second part, I'll take you through the applied example. So in the simulation assessment, we're going to look at how we define heat wave exposure across geographically diverse data. We'll look at what happens when we define heat waves based on absolute temperatures versus on percentile-based thresholds. We'll look at what happens when we model our temperature exposures as binary, so those threshold models versus continuous. And then we're going to look at how climate heterogeneity changes effect estimates across different makeups of city types. In the applied example, I'm going to show you an actual epidemiological example in real world data using the 1.3 million births in Arizona over this 15-year time period. We'll look at heat wave exposures from preconception through delivery. The outcome is a binary low 5-minute APGAR score, and we use distributed lag nonlinear models to identify the sensitive exposure windows. Okay, so this is ambient heat is somewhat similar to ambient air pollution in that it's kind of an instrumental variable. So we think that ambient heat is probably affecting perinatal health outcomes through changing personal heat or personal heat adaptation, right? And there are all these factors that are going to be affecting personal heat, right? Like time, activity outside, housing characteristics, maternal characteristics. And we have this fairly complex series of, we have a complex DAG, right? It's actually a lot more complex than this. And that force us to think about what variables we need to control for, what we don't need to control for, what's a collider, what's a mediator. But ambient heat, right, is not necessarily associated with any of these. It's just sitting out here affecting perinatal health through this variable. So it's actually an instrumental variable, which has some nice properties because it means it's sort of generally unconfounded by all of these variables. You might imagine that this is not necessarily a 100% true depiction. There are some other variables that are going to affect ambient heat, but they're going to be more global and they're not going to be these ones. So you might also think that ambient heat is actually affecting time or activity outside, but time activity outside is a collider here or a mediator. So you wouldn't actually want to control for time or activity outside in this instance. So ambient heat has some nice properties in epidemiological models when we are looking at it as compared to personal heat. Okay, so when we think about the physiological progression of heat exposure during pregnancy, and this is not necessarily unique to pregnancy, but certainly unique in that it has possible health effects for the fetus. So in stage 1, we have heat exposure, but the body is coping. There's some behavioral avoidance. The core temp is stable. Then we progress to heat stress, and the body starts engaging in active thermoregulation, and there are some bodily adaptations here. Then we progress to heat strain, where our core temp is rising, and we start to see potentially stronger effects on the fetus. And then we get to heat illness, which is an emergency. And so these are all examples of personal heat. These are health effects, and then what we are really modeling is ambient heat, right? So ambient heat comes before personal heat, before health effects, and just a simpler DAG here, ambient heat. Okay, so for when we're going through the modeling choices, when we're looking at the associations of heat exposures with a health outcome, there are lots and lots of different choices that we have to make along the way. So we have to choose between using absolute versus relative temperatures. So are we going to use these 100 degrees, or are we going to use 90 percentiles? Are we going to correct it for humidity? Are we going to just use temperature? Are we going to use a heat index? For heat waves, are we going to use a 3-day heat wave, a 4-day heat wave, a 5-day heat wave? Are we going to have percentile thresholds, 95th percentile? What thresholds are we using, 95th or 99th? For absolute temperatures, what thresholds are we using, 85, 100, 105, 110? Are we going to use the average temperature, average daily temperatures? Are we going to use the peak daily temperatures, the minimum daily temperatures, daytime, nighttime temperatures? What temperature model are we going to use? There's a lot of different models, and a lot have come out more recently, and they all have different advantages and disadvantages. When we do our statistical modeling, are we going to use a distributed lag model, or are we going to use some other type of model? Are we going to adjust for location in our data with heterogeneous locations? If we're doing it in pregnancy, do we need to use a risk set modeling approach to account for exposure windows across different gestational ages? I talked a little bit about this in the applied example. For outcome, are we going to use a binary model or a continuous model? And then for our sensitive window selections, do we use weeks of pregnancy? Do we use trimesters? How far back do we go for preconception, the preconception period? And then if we're looking at an acute event, do we look at the day before, the week before, years before? There are lots of different choices that have to be made. And in this simulation, just focusing on 3 things. So absolute versus relative temperatures, the thresholds for heat waves, and then whether or not we adjust for location in data with heterogeneous locations. And also we're going to be looking a little bit more at the specific mix of heterogeneous locations. Okay, so just a little bit more on absolute versus relative temperatures, because it's important that we understand this before we move forward. So in an absolute threshold, when we're defining a heat wave, we might say, okay, if the temperature is above 100 degrees, then that is going to contribute to a heat wave. And then for the heat wave definition, we say there were multiple days in a row with a temperature above 100 degrees, regardless of the location. And the advantage of using this threshold is that it might reflect a true human temperature threshold for heat strain and heat sensitivity, right? Core body temperature is pretty much the same across geography. And there's some other arguments that can be made actually for this. But the disadvantages of using an absolute threshold is that some cities are going to have 0 heat waves, and other cities are going to just be one long constant heat wave. So the exposure distribution across the cities looks pretty gnarly, and it's not ideal for an epidemiologic study. On the other hand, we have percentile thresholds. So if you can imagine the distribution of daily peak temperatures across the last year, the last 5 years in a given city, and we do a cutoff of the 95th percentile for this city. The 95th percentile lines up with 100 degrees Fahrenheit. Anything above it is going to be a heat wave. Anything below it is not a heat wave. And so here it's the same idea where we have multiple days in a row where the temperature is above the 95th percentile, regardless of the location. So you can imagine that in Phoenix, the 95th percentile might be 110 degrees Fahrenheit, whereas in Seattle, the 95th percentile might be 80 degrees Fahrenheit. So there's a large difference in the temperature. The advantages here, though, are that you have exposed people in every city. So there's a better distribution of exposures across the cities, including cool cities. And it's more helpful from a modeling perspective to have that nice exposure distribution. And it might reflect true human adaptation to a heat and climate. The disadvantages are that in a particularly temperate area, a heat wave might actually be 3 days in a row at 75 degrees Fahrenheit, which probably biologically doesn't make any sense and won't accurately reflect heat strain. Okay, so in a simulation model, you have to set some true value. You have to make an assumption about what is the true effect that you're going to compare everything against. So I assumed for this particular simulation that the biological truth is that the risk is a function of the daily maximum temperature. So you can imagine that below some temperature, as the temperature increases, there's no excess risk. So if we go to the extreme, if we look at the extremes, going from 33 degrees Fahrenheit to 34 degrees Fahrenheit, probably there's no increased risk of heat-related illness. If you go from and that's true, right, below some value. And then above some value, so on the other extreme, for instance, going from 104 degrees Fahrenheit to 105 degrees Fahrenheit, you probably do have some increasing risk with each temperature increase. And so the question is just, what is this cutoff? And so for the purposes of this simulation, I just use 85 degrees. So below 85 degrees, the risk is flat with every increasing degree. And above 85 degrees, the risk increases linearly with every increasing degree of temperature. So for the actual simulation, so we had that true effect. I assumed the baseline risk of an outcome was 5%. And that's because the APGAR score that I model in the actual applied example, the outcome is about 5%. And then we base it on average daily, I'm sorry, this got cut off, but it's based on average daily max temperatures during pregnancy. In all models, we used a sample size of 500,000. I calculated odds ratios. So I only estimated 1 week of pregnancy rather than doing an entire DLM. So I just wanted to see what happened during this 1 week, the 20th week of gestation. Assumed the births were distributed evenly across the calendar year, and I did 100 simulations for every combination of cool city type. And I'll talk about that in a second. And then we tested the continuous measures of exposures. So the number of heat degrees beyond 85 and the number of percentiles past the 85th percentile. We used binary absolute thresholds of 85, 100, and 105, and then the binary percentile thresholds of 85th, 95th, and 99th percentiles. And for standardization for the percentiles, just use the 5 years for that city for percentile calculation. I checked what happened when we adjusted for city versus did not adjust for city. And part of the city adjustment is because the percentiles are city specific. So I wanted to see what would happen or how important this was. And then for climate heterogeneity, this is driven basically out of this real world observation that the number of cool cities varies strongly from population to population. So here I tested each set of simulations in 0 cool cities, in what would happen in, every simulation had 10 cities. And so I tested what happened when we had 0 cool cities, 1 cool city, 2 cool cities, 3 cool cities, all the way up to 10 cool cities. So if you have 0 cool cities, that means you have 10 hot cities. If you have 10 cool cities, that means you have 0 hot cities. And there were just 2 city types here, hot or cold. And this will make a little bit more sense as I show you the outcomes. Okay, so this is what the temperature distributions looked like as the cool cities increase. So here, this panel is 0 cool cities, right? So this is all hot cities. And down here is 10 cool cities, so all cool cities. Here is the 105-degree cutoff threshold for a heat wave. This is a 100-degree threshold for a heat wave. And you can see that you have a lot of exposed people when there's 0 cool cities, a lot of people who are exposed to these heat waves here. And then the number of people goes down as the proportion of cool cities goes up. And so that by the time you get to 10 cool cities, you have almost nobody who's exposed to a heat wave. And then when you look at how that's driven by hot versus cool city, here the hot cities are in yellow and here the cool cities are in purple. And you can see that every single exposed person is coming from a hot city, right? And this is what we would expect based on what we see from our distributions. But these are using the absolute thresholds. When you look at the percentile-based thresholds, here you get a good number. These are percentile for each city. And here you get good distribution of people at the 95th percentile in hot cities. And you also get good distribution of people above the 95th percentile in cool cities. But the thing to note is that your people who are classified as exposed in a heat wave for a hot city, the absolute temperature threshold is going to be way higher than the absolute temperature threshold when you're using percentiles in a cool city. So you have to really, and then you have this huge number of people who would not be classified as exposed in a hot city, but would be classified as exposed in a cool city. All right, so we're going to go through these one at a time. So in here, we're going to look at the binary absolute thresholds and then the binary percentile thresholds. So here we have the absolute threshold of 100 degrees. So basically in this gestation, if you could imagine a pregnant woman during gestational week 20, if she was exposed to a temperature over 100 degrees for 3 days in a row, she gets a 1. If she was not, she gets a 0. And so everybody is a 0 or 1 exposed to this 3-day heat wave or not exposed to this 3-day heat wave. For the percentiles, it was the same thing, except we defined it based on the city-specific temperature percentile. So if they were over the 95th percentile for 3 days in a row, they got a 1. And we wanted to know how these vary from each other, from the true effect, and as the number of cool cities increases, and does adjusting for city matter? Okay, so these are the results. Here, this panel is using the 100-degree Fahrenheit threshold for a 3-day heat wave. This is using the 95th percentile threshold for a 3-day heat wave. The blue is going to be unadjusted, and the red is adjusted for city. And here is the anticipated true effect. The true effect is the dashed red line. So here under the 100-degree threshold, we can see that the anticipated effect estimates do change a little bit as the number of cool cities increase. And they generally are underestimates of the true effect here. And then for the percentile threshold, the thing that is important to note is that the true effect actually changes as the number of cool cities change. And this doesn't necessarily make sense until you think about it. So if you imagine 0 cool cities, right? So like, let's imagine a population just of a bunch of phoenixes. And the 95th percentile in Phoenix is going to be around 110 degrees Fahrenheit. And because risk starts to increase in our true biological model at 85 degrees, the risk for the adverse outcome at 110 degrees is going to be really high. Whereas in very cool cities where the 95th percentile might be 83 degrees or 84 degrees, then the true risk is going to be null at that amount. So as the number of cool cities increase, your true anticipated effect for the percentiles decrease. And this is somewhat ironic because some of the benefits of using percentiles are basically to handle large numbers of cool cities. But you're actually handicapping yourself because the true effect at lots of cool cities is really close to null. The other thing to note is that these confidence intervals these simulation intervals are really wide for percentiles and much tighter for the absolute thresholds. Okay, so then we wanted to look at what happened at the different cutoffs, so 85, 100, 105, and then the 95th. I think I also did the 85th and the 99th percentile here. So the same thing as the last slides, except now we're looking at additional thresholds. The thing to note here, just really quickly under percentile threshold, when we use the 99th percentile, this is the simulation interval for the 99th percentile, and it's just really wide, and it blows up our axes, so we can't look at things. And then also just, I want to point out that the 99th percentile is super variable and just not very precise, and it's just because it's a very rare exposure. So I just removed the 99th percentile so we could look at the effects a little bit closer. So let's start with absolute threshold. Here you can see the brown is 100 degrees and the green is 105 and the red is the 85th percentile. And the 85th percentile, 85 degrees. And 85 degrees tracks the true 85 degree effect pretty well until you get to about 10 cool cities. This is just because it's a random problem for a somewhat rare exposure here. And then, so the 85 degrees does a good job, and that's because the true effect starts rising at 85 and there's no risk below 85. So this is just a minimally exposure misclassified cutoff here. But for 100, and then this is the true effect for 100 degrees, and this is the true effect for 105 degrees. And so even though 105 degrees is more extreme, it's a much more dramatic underperformance of the true effect compared to 100 degrees. And similarly for the percentile thresholds, so again, the true effects for the percentiles decrease as the number of cool cities increase. And then the underperformance is stronger for the 95th percentile compared to the 85th percentile, although they're both still not great. And then performance really deteriorates as you get more cool cities. So basically, as you get more cool cities, percentiles actually underperform in a model where the true effect is based on absolute temperature thresholds. Okay, and then because we had the original biological model assumed a continuous effect, we also looked at what happened when we modeled these continuously. So if we look at the number of heat degrees beyond 85, so for instance, if you imagine the gestational week 20, let's say the average weekly temperature that week was 90 degrees, 90 minus 85 is 5, so that person gets a 5. If it was 91 degrees, they would get a 6, 92, they would get a 7, right? So it's continuous. And then the same thing, but for percentiles. So if they're in the 90th percentile, they get a 5. And basically you get almost a true performance here, and that's because we're modeling what we assumed to be true. When we're looking at heat degrees beyond 85 degrees, we get almost a perfect effect estimate that is consistent across number of cool cities. When we look at the percentile excess above the 85th percentile, we see the same pattern where the effect estimate decreases as the number of cool cities increase. I didn't put the true effect on here because it's actually much more complicated to model. We can talk about that if you guys want to, but I actually haven't 100% figured out how to model the true effect here because it's so complicated. Okay, so the conclusions for this are that using a continuous measure of exposure, the absolute measures, the degrees, are consistent across heterogeneous cities and generally less biased. The percentile measures were not consistent across heterogeneous cities and not comparable across populations. For the binary absolute thresholds, the 85 outperformed 105 and 100 in terms of bias. And when we're talking about the binary percentile thresholds, the 85th outperformed the 95th and the 99th. And that's just because of exposure misclassification. You're just reducing exposure misclassification when you use the correct cutoff. City adjustment was generally not really important in this model. It might have even biased results towards the null. And then for climate heterogeneity, the mixture of cool cities can dramatically affect estimates under certain modeling assumptions. So we have to be really careful about comparing interpretations of percentile-based effects when we're looking at heterogeneous mixtures of city latitudes, basically. So under these conditions, the most important takeaway is you should use absolute measures and not percentiles. Okay, but still unanswered. The true biological model is unknown. I don't know if 85 is right. I don't actually know if absolute temperatures are right compared to percentiles. It didn't look at heat wavelengths. There's a lot more DAG work that needs to be done for the percentiles, and a lot more methodological work needs to be done for modeling heat. Okay, so moving on to the applied example. So we know that heat waves in pregnancy are associated with preterm birth, low birth weight, and fetal growth restriction. We know that in pregnant mice and sows that heat stress can cause neurological damage and oxidative stress. Unfortunately, there's no perfect neurological markers that are widely used at birth. However, there is the APGAR score, and we'll talk a little bit about the APGAR score on the next slide. I think it's on the next slide. And this has been done in 2 papers outside the United States, in Colombia and in China, but they were looking at the last week of gestation or the 2nd and the 3rd trimester rather than across pregnancy and into the preconception period. So our goal for this applied example is to investigate the associations between sensitive windows of heat wave exposure during preconception and gestation with low APGAR score at birth using distributed lag models. All right, so the APGAR score is assessed at 1 and 5 minutes. A perfect score is a score of 10, and the APGAR score is predictive of neurological disability, including cerebral palsy and cognitive impairment in childhood. It's not 100% predictive, but it's a good early marker. So the score, APGAR stands for appearance, pulse, grimace, activity, and respiration. And the nurse performs various tests and then scores them with 0 points, 1 point, or 2 points per element here. And so in previous studies, they have used a cutoff for the APGAR score of either 7 or 8 to indicate a low APGAR score. All right, so we used the population-based study of 1.3 million births in Arizona from 2006 through 2021, part of the Arizona Pregnant Women's Environment and Reproductive Outcome Study. It excluded those with gestational age less than 28 weeks or greater than or equal to 42 weeks or non-geocodable addresses. And then we did a binary measure of the low APGAR score at 5 minutes after birth and just tested what happened when we used the 2 different cutoffs for APGAR. We got our temperature and our relative humidity data from NOAA's DayMet, which is modeled at 1 square kilometer across the contiguous United States. And it's based on ground-based measures. We looked at the daily max temperatures and we linked them from 28 weeks preconception all the way through birth. And we looked at heat waves. So we did a binary measure of heat. And so if the maximum temperature was greater than or equal to 42 degrees Celsius, which is approximately equal to, I think it's 107 degrees Fahrenheit, for 3, 4, or 5 consecutive days within a calendar week. We also created the heat index, which accounts for humidity. And we didn't consider heat waves longer than 5 days. And we, although they would have been coded as having a 3-day or 4-day or a 5-day heat wave. And then if you had 2 3-day heat waves in the same week, those were coded as a single 3-day, but this is pretty rare, super rare. For distributed lag nonlinear models has an interesting problem that has only been discovered, I would say, in the last couple of years when using it for using it during pregnancy. And the problem is that it requires a fully specified exposure matrix. So here we can see this person A, person B, and person C. They have gestational week 37, 38, and 39. And when you use the DLM and if you put all these people together, you have to have a heat wave identified for every week. But if you have a person who gave birth during gestational week 37, they would still be coded as having a heat wave for weeks 38 and 39, even though they had already given birth. And so the way we overcame this was we used a risk set model as described in Lung et al. 2024, where they described this really nice approach in EHP, where they separate everybody out into risk sets of gestational ages. And we used a meta-analytic approach to average the effects. And that's what these 2 lines basically say. We did that separately for each heat wave definition. When we defined our lag response relationship, we used natural cubic spline and we allowed knots at each trimester start date. And then we selected various covariates based on the literature. And then we modeled the heat waves using both true temperatures and then the heat index adjusted temperatures. These are the characteristics of our study population broken up by normal APGAR score and low APGAR score. So we had about 1.3 million people here. And you can see that males were slightly more likely to have a low APGAR score And there was a little bit of variation by education and a little bit of variation by race, but nothing too terrible. Okay, so these are the DLMs, and the way we can interpret this is this each dashed line going down is where the knots were. And then, actually, no, that's not true. Sorry, the dashed line going across is null, 1.0. The first panel is the 3-day heat wave. And then the second panel is a 4-day heat wave. And the third panel is a 5-day heat wave. This is 0, which means week of conception. And then -4 just means 4 weeks prior to conception, 8 weeks prior to conception, 12 weeks prior to conception, all the way back to 28 weeks prior to conception. And what you see is the confidence intervals are the tightest for the 3-day heat waves, and they get a little bigger for 4 and a little bigger for 5. And you can also see that preconception, we have this fairly stable increased effect estimate all the way back from about -18 weeks through about -6 weeks-ish. And then we also have consistent effect estimates throughout pregnancy all the way up until somewhere, the risk looks like it starts to drop somewhere in this 30-week range, right? So most of the risk is occurring in this preconception period and then early to mid-pregnancy. And this is when using the standard heat wave with APGAR score coded as under 8 as high risk. All right, when we use the heat index, which accounts for humidity, we see much larger confidence intervals. So it's not performing as well as the absolute temperature, although I think the risk might be a little bit higher. And here you see risk peaking in this -8, -9 window, but then also still this elevated risk up until about 30, somewhere in this 32-week range. When we use a sensitivity analysis where we use a stricter version of the APGAR cutoff, see similar interpretations here. And then this is when you use the heat index at that lower cutoff here, all of our effects pretty much go away, but this is probably just a power issue. Okay, so mothers exposed to heat waves in specific weeks during preconception and throughout pregnancy until about 36 weeks had a higher odds of having a child with a low 5-minute APGAR score. We know that the preconception effects peaked at about 8 to 20 weeks preconception. This could be because folliculogenesis starts around 12 to 18 weeks preconception, where the follicle matures from primordial to antral stages. But there's mixed findings in other controlled studies. For spermatogenesis, we did consider that preconception effects might not be the mom, right, but could be the dad because it's based on residence. And presumably, oftentimes the father lives with the mother. And but the sperm live a max of 10 weeks, so it wouldn't explain any of the findings that were more than 10 weeks preconception. But it could still be contributing in this 8-week window. And then there are some differences by day length. So there were 2 possible, so 3 days, 4 days, or 5 days. And so there were 2 possible interpretations. One is that maybe there's some intrinsic short-term adaptation. There's not a lot of literature on human temperature adaptation in that short-term time period. And there's limited data on climate control or behavior changes, especially in that short-term time period. It's probably a little bit more likely that it's a power or a modeling issue. So 4 or 5-day heat waves are rarer than 3-day heat waves. And also, when we modeled a 4-day heat wave, everybody who was exposed to a 3-day heat wave, but not a 4-day heat wave, is incorrectly specified as having no exposure when we know that there was increased risk at that 3-day heat wave. So it's probably just an exposure misclassification issue. Okay, so we do know from animal studies that gestational temperature exposure as low as 35 degrees can disrupt heat shock protein and impact neurological development. And we also know that thyroid hormone production starts to be affected under heat stress, which can cause lots of downstream health effects. Our next steps are to start incorporating some housing data based on assessor data to look at how housing quality might affect some of these, might affect resiliency towards some of these heat effects. So looking at it as a modifier, and then looking at some of these other community level variables like the NDVI, the canopy cover, land use, and then actually looking at municipal policies around heat resilience to see if that helps mitigate some of the effects of ambient heat. Some overall recommendations when thinking about the findings across both the simulation and the applied examples. So for heat wave definitions, lower thresholds might be better. So that might include shorter heat wave definitions. So for instance, using a 3-day heat wave as opposed to a 4 or 5-day heat wave, and maybe even a 2-day heat wave, and including less severe temperature cutoffs. So 85 degrees as opposed to 105 degrees would have been suggested by the simulation, although in the paper, we use this stronger 105-degree temperature. We also note that absolute temperatures might outperform heat index or percentile-based temperatures. Preconception appears to be important and should be included in most of these models, going pretty far back. And then from the simulation only, the continuous measures of exposure might be a better reflection of underlying biological reality compared to the threshold in the binary models. Okay, and I just want to acknowledge the team of investigators and all of the students and staff that helped, and also the funding from NIH that made this possible. Okay.
Thank you. That was really impressive and very interesting. And I always find these talks that are very much outside my area of expertise. Just fascinating in the in how climate can have just so much impact in various components of health, from in vitro to all the way from birth to time we age through the life cycle. So John, you have a question?
Hi, yeah, actually that was a really cool talk. I really enjoyed that. It's terrific. On one of your earlier slides where you're talking about using the threshold of 85 degrees, I think you indicated, I don't know if you said it or, it certainly kind of looks that way on the slide, that, the risk increases linearly with temperature. And I was kind of, and maybe you answered this later in the talk, because you did mention something about using spline modeling with knots. But is there justification for that assumption that that there's a linear relationship, or is that just kind of a simplistic diagram? Because I would not expect it to be linear.
You mean, yeah, you would expect it
That
to
risk.
be maybe more exponential?
Yeah,
Is that right?
exponential or possibly even just inconsistent, in part based on, there's a function, as you certainly alluded to, of gestational age, susceptibility. But yeah, I think that, what I would expect is, most susceptible would be affected early on, which is a smaller population. But as the temperature increases, a larger and larger portion of the population is going to be increased till, you get to a temperature where everybody's was suffering in some way. And so, I think, I don't know if it's necessarily exponential. I was just kind of wondering what that relationship really looks like.
Yeah, so this might be exponential, but this means that, this reflects population average effects, right? So like at 86 degrees, the increased risk is, the odds ratio is 1.005, right? Which means that for any given person, the increased risk is 1.005. And then as you increase your temperature, your risk of the adverse outcome gets really high, right? So like here, I don't know what this is, but if this was 95 degrees, then your risk would be 1.05 as opposed to 1.005. So it does account for like an increased prevalence of the population being at increased risk as the temperature goes up. But this is a really simplistic model, and it was just because I had to choose something to model as the underlying truth. So I thought that this was closer to, with sort of this threshold effect, it was closer to the biological truth than, right, risk just increasing linearly like this, right? Can you see my cursor?
Yeah.
Okay, then risk just increasing linearly, like from 0 degrees through 85 degrees, right? An exponential model would be interesting, but I think nobody really knows like what the true shape of this population line looks like. A lot of people do use 85 degrees as the cutoff for increased risk, and you do start to see some compensatory mechanisms happening at 85 degrees. I know personally that like I won't run outside if it's more than 81 degrees because I just hate being hot. But
Yeah, it's
the
pretty hot.
85 yeah, but the 85 degrees comes from the literature, and this comes from sort of kind of like a best guess, or it was just the basis for comparing how percentiles and temperatures model. So like the shape of this doesn't actually really matter, if that makes sense, for answering the question of percentiles versus temperature.
Okay.
How does, I was going to say, how does humidity enroll? I know Arizona has no humidity out there, and you can just purely go with the temperatures. But in Cincinnati, we certainly have humidity as a big concern. And how would that impact this line?
Yeah. So, well, this line. Yeah, I mean, you could interpret this as being absolute temperature. You could interpret it as being a heat index temperature that incorporated humidity. There is a lot of evidence that humidity absolutely affects susceptibility to heat stress and heat strain. In this simulation model, I did not include heat index at all because we're just trying to keep it super simple. But in the APGAR score paper, which is under review right now, we did look at how the heat index variables compared to the heat wave, just the absolute temperatures. And in Arizona, most of the time it's just very dry. There's there's no humidity. But during monsoon season, which is like a 2-month period, we do get a lot of humidity. Well, a lot. It goes up to like 40%, which is not the same, 95 degrees. And it's also pretty geographically diverse. So we can take advantage of the spatial distribution and the temporal distribution, right, to look at how these heat wave, the heat index affects different things. But what we just saw was just this increase in the confidence interval. So I think I had expected the heat index to outperform the heat wave, but it didn't. It didn't. So, I mean, it's still significant in the using the more generous method of the APGAR score definition, but we still get these much larger confidence intervals when using the heat index.
George?
Yes, that was a fascinating talk, and I realize how hard it is to model heat. That is very clearly so compared to air pollution, like you mentioned at the beginning. And the one thing I think is important to note is that air pollution continues to go down, like PM 2.5 in most places, but heat's going to continue to go up. And so when we compare the two, the risk for heat of the future is something that we need to be concerned about. My question to you is about gestation. The APGAR score must be linked at times to when the brain is developing during gestation, or the peripheral nervous system is being developed. What's known, I mean, there must have been other types of insults that have been noted to alter APGAR scores. And during what period of gestation would they be the critical windows?
Yeah, so I mean, I think when most of us are thinking about neurological outcomes, we like to think about the third trimester as being potentially the most susceptible because that's when most of the brain growth happens. But earlier during gestation, you've got a lot more cell division. So like an insult to a cell might have much more impact on downstream cells if it happens earlier compared to later. So we've done a lot of trimester specific assessments for pesticide exposures during pregnancy, and we actually see a lot for preconception and first trimester actually, and less for later. I don't know how consistent that is with necessarily other types of environmental exposures. I know that for air pollution, for instance, I don't know the air pollution APGAR literature, but I do know that for air pollution, the gestational weeks can be pretty variable. There's a lot of evidence, in the second trimester for neurological outcomes generally. But it's really hard to figure out what a good hypothesis for what we would assume a sensitive window to be, just because there's an argument that could be made for across gestation for the different sensitive windows.
Ahmet?
Thank you very much for an outstanding presentation. One quick question is, did you measure their core body temperature? Not.
No, we did not measure core body temperature. So we just have, because we had 1 million births, and we're just using observational data, so we don't have access to the individual level data. And that's personal heat, right? So, and we were looking at ambient heat, challenges for ambient heat.
With the new technology available, you can use a sensor called bioharness, which actually is attached on the skin, but it gives you core body temperature of any person.
Yeah, but these people were not actually enrolled in a study. This comes from administrative health record databases. So these people were, these people gave birth back in 2016. And so we're using these retrospective models. But I do think that and using personal heat is like a completely different sort of beast when it comes to epidemiological models and has its own set of challenges. But you are closer, right, to the health outcomes. So I think that would be, for a birth cohort that is ongoing right now and can measure core body temperature, I think that would be really extremely valuable information, especially in providing information about how heat resiliency varies. Resiliency to ambient heat varies from person to person. So I think that would be really important. It's just that we don't have any of that ability because these people have already given birth.
Okay, I understand. I think in the future, if you do a birth control, then having a biosensor would be very helpful, because I have used birth cohort in our children's study with their children, and they are exposed to lead, for example, in 1950s. And we're actually seeing use of the bioharness now is available. Is very useful information. But I'm just talking about in the future, if you want to think about it.
Yes. Yeah, for sure. If I am so inspired to enroll a birth cohort, I would definitely measure biosensors or use biosensors for temperature.
Thank you.
I don't see any others. Well, thank you very much. I guess it was an amazing talk. Greatly appreciate that you presented, and good luck in your continued research. And
all right. Thank you, Kermit, and thank you everybody for listening and asking such great questions. It's been a while since I've gotten such good questions for the seminar.
all right. Well, thank you. Have a
Thank you.
great rest of the week.